Hello, everyone. Welcome to this MECHS webinar. Today, we are lucky to have Dr. Nicolaus Socanas discussing the topic of real-time and stochastic hybrid simulation. Dr. Socanas received his diploma from the Faculty of Electrical Engineering and Computer Science at the University of Patras in Greece. Afterwards, he joined the Chair of Structural Dynamics and Earthquake Engineering at ETH Zurich in Switzerland as a doctoral student. Dr. Socanas is a Marie Curie Fellow, and his research work is part of the European Union's Horizon 2020 program entitled Divert. During his PhD, Dr. Socanas visited and conducted part of his research work in the Dynamics Research Group at the University of Sheffield in the United Kingdom, and also in the Model-Based System Testing Group at the Siemens Digital Industries software in Belgium. Today, he will be presenting an overview of his doctoral thesis. There is going to be a question and answer section at the end of the presentation, so please hold off on your questions until the end. Now, please, let's welcome Dr. Socanas.
Hello, everyone, and thank you very much for the introduction, Edwin, and thank you very much for giving me the opportunity to present an outlook of my PhD thesis here today. My PhD thesis is entitled Real-Time and Stochastic Hybrid Simulation, and today I will give an overview of the activities that we did and some results that we obtained. It's supervised by Professor Božidar Stojadinovic, and it's founded from the European Union Horizon 2020 Marie Curie program called Divert. So to start with, here you can see the outline of my presentation. I'm going to begin talking about the motivation behind this research project. Then I will address the research objectives of this project, which are two. The first one is real-time hybrid simulation, and the second is to extend this one to a more stochastic version. I will talk about the methodologies that we used and some case studies that we investigated, as well as some indicative results that we obtained. And finally, I will conclude with some conclusions and future research directions. So to begin with, what is the motivation behind this research project? So it's often the case that prior to any engineering decision, we may consult a high-fidelity model in order to give some insight to the performance of the exam structure, but to also account for any potential risks that are embedded in its design. Therefore, the overreaching goal is to develop some trusted models of uncertain engineering structures that operate under uncertain conditions. And this process is what we call dynamic virtualization. However, in order to create such trusted models, as you may know, it's essential to go through the process, the so-called process of verification and validation. And today I'm going to talk basically about validation. An experimental, a key element of validation is the experimental testing. And in structural engineering disciplines, we often come across three popular, let's say, test techniques. The first one is the quasi-static test, which is the simpler to conduct, at least in comparison with the other two, but it can be restricted to the nature of the predefined imposed loadings. On the other hand, we have the full-scale physical dynamic testing, with which we can get quite realistic outcomes, but the associated experimentation costs can grow significantly, and this is the case because we don't have only to build a specimen full scale, but we also need to have the appropriate experimental equipment that will be capable enough to test such large full-scale tests. And then another alternative is the hybrid simulation, which corresponds to the whole part of this project. And basically, it combines the flexibility of numerical simulations with the realism of experimental testing. Essentially, it offers a cost-effective alternative to full-scale physical dynamic testing. So let's see in a few words what actually hybrid simulation is. Imagine that we have this reference full-scale system denoted by R. And then if we would like to test this system under the hybrid simulation approach, we would need to decompose it to numerical and to physical substructures. Then the numerical substructure will be simulated numerically in a computer, while the physical ones will be built and tested physically in a lab. Then during the hybrid simulation, in every time step of it, we will need to ensure that the boundary conditions between the numerical and the physical substructure are synchronized in order to guarantee high fidelity results. And we also need to obey some compatibility and equilibrium conditions. Finally, we can select some variables of the hybrid model in order to couple those two substructures. And the selection of these variables is most of the cases application specific, project specific. But in structural engineering, we come often across displacement of force, or maybe we could also see velocity and torque, etc. Let's now see some hybrid simulation examples. I'm sure that many of you have seen this one as it comes from the benchmark problem from the MECHS community. So let's say that we have this reference full-scale system, which is a three-story structure. Then if we're particularly interested, let's say, in part of the first story, this then could correspond to our physical substructure, while the rest could represent our numerical substructure. Then the fusion of the two, the combination of the two, will form the so-called hybrid. And then in every times of the simulation, we will need to ensure that the boundary conditions between those two will have to be synchronized in order to ensure high fidelity results. Another example from another engineering discipline is this motorbike. Let's imagine that this could be the reference scale system. Now, if we're particularly interested in the transmission of the motorbike, then this could represent our physical substructure, built and tested physically in the lab, while the remaining of the motorbike be numerically simulated. And then again, the fusion of the two would form the hybrid model. But this brings us to the question if the actual hybrid simulation outcomes are reliable. So we're basing our assumption that by decomposing our reference full-scale system into numerical and physical substructures, and by only testing physically the physical substructure, taking into account the interconnection with numerical ones, we can have a cost-effective simulation technique alternative to full-scale physical dynamic testing. However, in order to have this assumption valid, we will need to make sure that the response of the reference full-scale system would actually be quite close to the response of our hybrid model. And this point drove our motivation for the first research objective, which is how we can conduct hybrid simulations of high fidelity trust. And it's often the case that we will need to do hybrid simulation in real time to achieve this. Nevertheless, when we try to do that in real time, we may come up with several challenges that we need to overcome. And the exact objective of this first research objective is what methodologies can we develop to overcome such challenges. Once this is accomplished, we can move forward to the second research objective, which is to extend the state-of-the-art deterministic hybrid simulation to more stochastic version. And by this, I mean to account for the stochastic nature of uncertain structural systems. And the motivation behind this is that it happens often that we may not know some parameters of our hybrid model, for example, the damping structure, some boundary conditions, as well as the excitation, which is most of the case stochastic. These are things that we do not know, or we do not know at a certain level of confidence. And therefore, it's important to understand how these associated uncertainties can propagate and how they can affect our system's dynamic response. And essentially, what we want to achieve is to unveil the structural sensitivity of the prototype structure to these input uncertainties. And then outcomes of such studies can assist not only in the design phase of structures, but also in the design phase of future experimental campaigns. Sorry for that. So to begin with the first research objective, the real-time hybrid simulation. So here we can see a typical block diagram of a hybrid model. On the one part, we would have a numerical substructure which is simulated in the computer, while on the other part, we will have the physical substructure, which is built in the lab. Then during the hybrid simulation, let's say that we have a predefined time history, but it excites a numerical substructure, and due to this excitation, we compute the response of our numerical substructure, denoted, let's say, by R, and then we need to transfer this signal, this energy, to the physical substructure, and then we measure some points of interest, we feed them back to the numerical substructure, and by that way, we couple those two. However, since this is in a computer and this is in a lab, we need a transfer system to transfer this signal. And this is most of the cases an arrangement of actuators or motors. Let's see an example that this R signal here from the numerical substructure can be denoted with this blue dust line here. Then if we just send this signal through our transfer system, what we will actually get is this red line. And as we can see, we have some time delays as well as some tracking. And recall that in every time of the simulation, we will need to ensure that the boundary conditions between the two will have to be synchronized. However, that's not the case for this example here. Therefore, a first challenge in real-time hybrid simulation originates from the physical substructure, and in particular from the transfer system that we are using. And the way to overcome this challenge is by introducing a tracking. So by doing so, we managed to compensate for these errors and delays, and instead of the red signal, we now have this yellow. And this is indeed much more close to the original one, and in that way we can synchronize the boundary conditions. Towards this direction, in this research project, we investigated two different control schemes. First one is based on model predictive control, or MPC in short, along with the Kalman filter and the polynomial extrapolation algorithm. So the objective of the controller is to provide a tracking control, compensate for time delays, and at the same time be robust to uncertainties and disturbances that may be introduced during the hybrid simulation. We also verified the performance of the controller with two case studies, and the results were promising. A few words regarding what MPC is. MPC is an optimal and robust control method, and in its core lies basically in optimization. So what we try to do is to minimize an objective function. And this objective function is actually embeds the tracking error, the error between our reference signal and the measure. So the designer can specify some group of time steps, and in every group of these time steps, optimization is being done within the simulation while the simulation is running, and then due to this optimization, a new control law is being derived. So although new control laws are being derived within the same simulation, the controller itself is not adapted yet, since the controller structure remains the same. A promising feature of MPC is that the designer can specify some hard constraints to be met during this optimization. And this is particularly important when we have to deal with experimental testing. And so with hybrid simulation, because we have to deal with experimental equipment that have limited capacity, and therefore we need to respect such constraints. So all in all, an MPC consists of four components. We have the prediction model. The prediction model is a model used internally in the MPC in the optimization, and basically it reflects the dynamics of the control plant that we want to control. Then we have the cost function, the constraints, and the optimizer, and basically the optimizer performs the optimization. So in classical MPC, we use a linear prediction model in order to reflect the dynamics of control. And if this linear model can approximate fairly well the dynamics of the control plant, then the performance of the MPC is also fairly good. However, for the case that we have a nonlinear control plant, or even a linear but with time-varying parameters, then just a linear prediction model would not be enough to provide MPC with the adequate performance. And this is what triggered our motivation for the next control scheme that we investigated, and this time it's based on an adaptive MPC. So the concept is more or less the same as before. What changes in this case is that during the simulation, before we are actually doing the optimization, we try to identify the changing control plot dynamics. And therefore, by doing so, we came up with a new model of the plant in every time so that we do the optimization, and we update the prediction model that it's being used internally inside the MPC. We also used one case study to validate the performance, and again, the results were promising that it would be successful. Moving on, so far I talked about challenges coming from the transfer system itself, but we may have also challenges coming from the numerical substructure when we want to conduct type simulation in real time. So recall this block diagram again, but now let's imagine that instead of only one numerical substructure, we have several. And now let's assume that maybe one more or maybe all of them are quite high dimensional and complex. And then in order to adequately capture the dynamic behavior, we would need to decrease the time step of the simulation. However, by doing so, we also increase the computational power that it's necessary to compute. And in real-time simulations, as well as in real-time hybrid simulation, when the actual computational power becomes larger or even close to the actual simulation time, then we may introduce time delays. We may also risk to distort the time scale of the simulation. And in the end, we may risk to falsify the results and the fidelity of the overall hybrid simulation. So in such cases, the only viable solution is to reduce the complexity of such high-dimensional numerical substructure. And the way we tackle this challenge is by working on a modular reduction framework, trying to identify these critical components and treat them as black box. And therefore, we approximate their dynamics with some simpler to evaluate functions, and the methods that we are used to do so are based on polynomial Gauss expansion, or PCE in short, and neural network methods. To elaborate a bit more on this framework, let's see this case study. Again, let's imagine that we have this motorbike as our reference full-scale system, and then we decompose into numerical and physical substructure. Then the transmission of the motorbike is our physical substructure, and all the rest will be our numerical substructure. Here we can see a block diagram of our hybrid model. Here you can see the transmission of the motorbike, physical substructure, and then we have four numerical substructures: the engine, the motorcycle void dynamics, and the real front wheel braking system. Now we identified that the real wheel and front wheel braking systems are quite complex since they incorporate the hydraulic dynamics of brakes, and therefore we train one PCE and one feed-forward neural network for each one of these two. And the goal is to substitute the full order model with one of these two reducer models. To test the framework, we define four testing scenarios. First one corresponds to a baseline scenario in which we test the hybrid model in its full order form. Then in the second scenario, we replace the full order model of the real and the front wheel braking system with a PCE, one for each one of the two. The third scenario is more or less the same, but instead of a PCE, we are using a feed-forward neural network, one for each one of the two. And in the last scenario, we do a mix. So we use a PCE for the real wheel and the feed-forward neural network for the front. And the motivation behind the last scenario is to actually see if we can combine both of these two techniques within the same hybrid model. And now here we can see some indicative results, some indicative hybrid model responses evaluated using under these four testing scenarios. As an overall remark, we can say that we managed to reduce more than 50% computational time by only replacing 2 out of 4 numerical substructures without losing so much into absolute accuracy versus the full order. So with that, I would like to conclude the first part, the real-time hybrid simulation, and move forward to the next one, which is the actual stochastic hybrid simulation. So recall that the idea behind this objective is to understand how specific uncertain parameters affect our overall dynamic response, some quantities of interest of our dynamic response. To do so, we were working on an uncertainty quantification framework, which consists of 4 steps. And the overall goal of this framework is to conduct global sensitivity analysis. So in the first step, try to identify the source of uncertainty. And with this, I mean that we select parameters of our hybrid model whose variation we want to investigate. After we have done that, we can assign to them some known probability distributions, and based on these distributions, we can generate some samples out. Then in the next step, for each set of these parameter sets, we can run one full hybrid model, hybrid simulation, and collect our quantities of interest. And in essence, what we are doing is to propagate these uncertainties throughout our hybrid. Nevertheless, in order to conduct properly global sensitivity analysis, we would need several of these points. And in essence, we will need several hybrid simulations. However, when dealing with experimental tests, this is not easily affordable, and therefore we had a problem. And the way to overcome this problem is by using the so-called surrogate models. So what we are doing is to generate as many points as necessary in order to develop an accurate surrogate of the initial hybrid. And once this is done, and we are confident that the surrogate model can replicate the analysis of our initial hybrid model with low validation error, then we can use this instead to generate all the necessary points needed to conduct actual sensitivity analysis. Conduct the sensitivity analysis, we do it by using the Sobol indices. And for the surrogate modeling, we are using 3 different techniques. The first one is the polynomial Gauss expansion, or PC in short, rigging, and polynomial Gauss rigging, or PCK in short. Let's now see one case study. Here we have our reference structure, which is actually a beam element with some linear restraints on the boundary conditions on the supports. Decomposing this to hybrid model, we have the beam element as the physical substructure, and then the boundary conditions on the supports as the numerical substructure. Then step 1, we select our uncertainties. In this case, the excitation, the hybrid model is it's a mechanical excitation, and the input uncertainties are coming from this one. We have we select the amplitude and the frequency of excitation, and also we select as input uncertainties the values of the boundary conditions on the supports. So we have in total 4 input parameters. Then the quantities of interest are the maximum rotation and maximum bending moment on the left support. Then we generate 200 points, and for each point we run one hybrid simulation, and with the collected data we can train one PC, one rigging, and one PCK for each of the 2 quantities of interest. And finally, once we are confident that these 3 surrogates are accurate, we can proceed to the last step, the one of sensitivity analysis. Here we can have a look on the testing that is being used to run this hybrid simulation to collect these points. Here we can see the beam element of the physical substructure, and here we can see 4 actuators which are actually controlling the boundary conditions on the left and on the right side. So here we can see the results of the sensitivity analysis. Here on the x-axis, we see the input uncertainties and the total Sobol indices for each of the 2 quantities of interest. In both cases, we can observe that the most dominant parameter is the frequency of the mechanical excitation. What we can also observe in this slide is that when we are computing Sobol indices using those 3 different surrogating techniques, then the results are not so different with each other. An important remark is that once a PC has already been developed, then the Sobol indices can be computed as a byproduct of the PCF coefficients at no extra computational cost. And that's not the case though for the PCK and rigging. And the way to compute the Sobol indices in these cases is by running some Monte Carlo simulations. So to recap this case study, we managed to compute some accurate surrogates using 3 different techniques, and then through sensitivity analysis, we managed to unveil the inner workings of the prototype structure to these uncertainties. However, we consider only uncertainties coming from the numerical substructure and from the excitation, the hybrid model. Therefore, we assume that the response of the physical substructure is deterministic. However, that's not a realistic scenario, as in reality, nominally identical specimens do not have identical responses. And therefore, this triggered our motivation for the next case study that we investigated, in which we consider stochastic physical substructure. Now, in order to make a stochastic surrogate model, we also use a different, the one of generalized lambda model. One case study for this case, the reference structure is more or less the same as before. However, now apart from a mechanical excitation, we also have a thermal excitation. The temperature fluctuations of this thermal excitation is considered, it's assumed to make the hybrid model response stochastic. As before, the physical substructure is the beam element and the numerical substructures are the boundary conditions on the surface. Step one, the input uncertainties are coming from the mechanical excitation again, the amplitude and the frequency. Now we also consider the maximum temperature of the thermal excitation, the maximum temperature of the flow, as well as before the values of the boundary conditions on the surface. In this case, our point of interest is the maximum out-of-plane displacement measured in the center of the plane. Again, as before, we do 200 hybrid simulations, and with the obtained data, we train the generalized lambda model. It's important to remark that an advantage of using the generalized lambda model is that we can train a stochastic surrogate without need for replication. We only need replications for validation. To make this more clear, our experimentally designed points include 200 points. In this slide, we can see some results for two specific points, this one. And then for each one of these points, we fix our input parameters to these experimental design parameters. And basically, we do 10 replications with fixed input parameters. And the response, you can see here with crosses x-axis, is actually different every time. This is an indication that our dynamic response is actually stochastic. These figures serve also as validation in order to validate if our generalized lambda model can predict these stochastic dynamic responses. And we see in these cases that the results are fairly good, and therefore we are confident that this is accurate, the surrogate is accurate, we can proceed to the last sensitivity analysis. But as I said before, since now we have stochastic physical substructure, we cannot use the classical Sobol indices, and therefore we are using an extension of them, the so-called quantile-based Sobol indices, and in particular we are using the 5, 50, 95% quantiles of our quantity of interest. And here you can see some results regarding the first order and total order Sobol indices. In the x-axis, we can see the input uncertainties. And for this specific case study, our most dominant parameter was the maximum value thermal excitation, of the thermal excitation. So coming to conclusions, in this research project, we had two different research objectives. The first one was how to deal with challenges that are arising when we want to conduct hybrid simulation in real time with the overall goal of increasing the fidelity of the results. And to tackle such challenges, we worked towards a model or reduction framework, as well as we developed two different types of control schemes. On the other hand, the second research objective was to investigate and to extend this concept to a more stochastic version, to more stochastic hybrid simulation. And for that, we worked towards an assertive quantification framework using surrogate modeling techniques and sensitivity analysis. Therefore, a combination of those two can provide us with a cost-effective and high-fidelity tool for model validation and calibration of uncertain engineering structures operating under uncertain conditions. And this is aligned with our overall goal, the one of dynamic visualization. Some future research direction regarding the first research objective would be to investigate how multiple model controllers coordinate and can perform within the same hybrid this has to do when we have to deal with multiple degrees of freedom physical substructures. Another point would be to investigate if it's possible to conduct hybrid simulation using variable time step. And this is more aligned also to the multi-rate concept of hybrid simulation. And the motivation behind this would be to be able to capture discontinuities in the system response. For example, in Rocky, when we have the impact, in order to adequately capture this phenomenon, we would need to decrease the time step in this particular moment. And then if we were about to conduct hybrid simulation with fixed time step, this wouldn't be so easily possible. Some research direction regarding the second objective would be towards the active learning concept of the input parameter space. And the idea would be to try to find the optimal and minimum experimental design point, and in essence, to find the minimum number of points that we have to use in order to compute an accurate surrogate model for sensitivity analysis. Also, a final point would be to investigate case studies with dependent input variables, as in the case studies I presented before, we assume statistically independent variables, and this is actually not so close to a realistic scenario. Here you can see some peer review articles that were derived from this PhD thesis. And with that, I would like to thank you very much for your attention. Acknowledge once again the founding from the beginning and welcome any questions that you
have. Thank you, Dr. Socanas, for your presentation. Now the floor is open for questions. So if you have any questions, you can unmute your microphone, or you can type it on the chat and I can ask them. There is already one question. It reads, great presentation. I have a question about uncertainty. Did you consider the uncertainty separation, aleatory and epistemic, in your uncertainty analysis and sensitivity analysis?
Actually, this has to do with how you interpret these parameter variations. For example, some variations in the mask would be aleatory uncertainties. So, for example, these input uncertainties could be grouped like that. And then also in the second case study, when we examine this internal stochasticity, the physical substructure, the stochastic physical substructure, is something that we cannot characterize nor control, and therefore, in such cases, we assume that this is something as systemic or due to some of these temperature fluctuations, the thermal excitation. So we didn't really group the uncertainties, but it's a matter of I think there is also another question about the time delay compensation approach. What time delay compensation approach did you use with the adaptive MDC controller? So the compensation was based on the controller was based on adaptive MDC, Kalman filter, and this model online modification algorithm. And the controller, the MDC, was trying to minimize this error, this tracking error between the reference and the actual measure. And in essence, it tried to minimize the time delay and also the tracking error, how different it is from the values, the one value to the other. I'm not sure if that's what you asked. Did this answer your question?
Another question reads, does the nature of the training sets must change according to simulation conditions, or the training sets were varied enough to account for multiple simulation conditions?
So the training sets, the bounds of the input parameters were defined in order to be able to operate the hybrid model in its linear regime. And this is because otherwise, if we do some damage to the physical substructure, we will need to change it every time we do a new hybrid simulation. And therefore, this would increase a lot the overall cost conducting the 200 hybrid simulations. And therefore, on the one hand, we identified these bounds so that it fits our overall objective, but also at the same time that do not plastically damage the physical substructure, so that we can reuse it. But we assumed, if I remember correctly, around 20% coefficient variation. I'm not sure, I don't remember exactly the numbers, but it should be on the responses.
Okay, another question is Sobol sensitivity analysis only applicable to statistical independent parameters?
No, there are methods developed to also, when you also have dependent input variables. However, you cannot use the classical Sobol indices. You have to use an extension of them. But this is possible, and there are Sobol indices available in the literature that you can use, and they deal with dependent input variables.
Another question that we have is, what do you think are the advantages of surrogate models in RTHS dynamic substructuring? And since RTHS is to study systems you don't know, how will you know when a surrogate model is sufficient for the purpose intended?
I think that there are several advantages when using surrogate models within real-time hybrid simulation. On the one part, you can use it to surrogate a high-dimensional model and therefore use this surrogate within the hybrid model. And this, the advantage of it is that when you have high-dimensional models and you reach to distort the time scale, in these cases, you can really use a reduced model and get rid of such risk. On the other hand, when you use it as the third quantification for sensitivity analysis, you can use it to emulate the overall dynamics, and then you use it offline after the simulation for sensitivity analysis or for other purposes that you define. But yes, basically, you may end up to a point that you have to develop a surrogate for a model that you do not know so well. So therefore, you have to, I think you have to run some simulations of this expensive initial model in order to understand the dynamics of it and which regions you need to, which area you need to take your training set in order to capture properly the dynamics. And of course, in the end, I think you need to define some validation error after which you are confident that surrogate can emulate fairly well the original initial. But I think you will always have an error, and in the end, it matters how much is it, but you know it, and if you are satisfied with this survey. Are there any other questions, maybe?
Well, if there are no other questions, thank you, Dr. Socanas, for your presentation and your answers. And that's all the time that we have for today. And we look forward to have you again with us in future presentations.
Thank you very much for the invitation, for giving me the chance to present my PhD thesis.
Thank you. And just a little reminder for the attendees, remember that you can send an email to mecs@purdue.edu to subscribe to our announcement lists. I just dropped the email in the chat, and other than that, thank you all for coming and have a great day.
Bye-bye.
Bye.
Bye, Nikos.